next, we're going to move into the next item on our agenda, which is the session 1, which is chaired by Gwen. And session 1, I believe the first presentation is Kelsey Gray from Insight Policy Research. And I'd like to welcome Gwen, the chairperson, to take over now.
Hi, I'm Gwen. I assume you can see me, Mike, is that right? Yeah, great. Okay, so I'm super excited about these next lot of presentations. It's about visualizing and visualizations and big data. So our first speaker is Kelsey Gray, and she's going to be talking about visualizing the impact of COVID-19 on WIC.
Great, thanks, Gwen. Hopefully someone will jump in if you can't hear me right now, but good morning. My name is Kelsey Gray. I'm the Associate Director of Data Science and Analytics at Insight Policy Research. And part of my work in that role is leading dashboard deployments for our federal clients. So we work with a number of different federal clients and agencies. And this presentation that I'm going to share in just a moment is part of a collaboration, a joint project that we did with the National WIC Association and 5 state WIC agencies to analyze the impact of COVID-19 on program participation and redemption patterns very early on in the pandemic. We started this presentation, or this kind of process, in March, and each month have been updating data from these state agencies to show trends over time related to how program participation has changed. So the 5 state agencies that we worked with are DC, Idaho, North Carolina, Vermont, and Wyoming. So very different state agencies spread across the country with different WIC participation population characteristics and different sizes of their total enrollment. One of the things we did, and I'll pull up the dashboard in just a moment, is that we asked these WIC agencies to share data that was readily available. So what you'll see when I share these dashboards is the information looks a little different across all of these state agencies, because we wanted to make it easy on them and make something useful for these state agencies. So it was an opportunity for us to understand what these state agencies needed to visualize their data, and then give them an opportunity to kind of understand what was going on in their programs. And for those who might not be familiar with the WIC program, it's the Food and Nutrition Services Women, Infants, and Children Special Program. I'll pull up my slides now and give a little more context to what WIC is. But I'll note that this dashboard is publicly available on Tableau Public. For those who might not be familiar, Tableau is a data visualization software similar to Microsoft Power BI or ClickView or other tools. So I'm going to go ahead and move forward with sharing my screen. Hopefully folks will let me know if they cannot see my screen. And I'm going to stop my video while I walk through this. Okay, great. So what you're seeing on your screen right now is a data visualization that we designed in Tableau, as I noted. What you're looking at right now is the landing page of this dashboard. So this dashboard gives folks who might not be familiar with WIC a little context for what the program is. WIC is a program that provides nutritious foods and other benefits to low-income families. And we were curious if all of the surges in unemployment and just the surge in cases have affected how the WIC program operates in these states. So over 6 million women, infants, and children participate in WIC on an average month. This view that you're seeing right now is a chloroplast map that shows for each state how many participants are participating in WIC. And so we designed it so that if you hover over the states, you'll see information related to how many participants were in WIC. This data is from the Food and Nutrition Service. It's a little delayed, so it's April 2020. We have more recent data for all of the state agencies that participated in this project. So a user can kind of hover over this information and just see how many WIC participants were in those states, and then click to view the direct source hyperlink. One of the things we did that I think is a nice visual trick when you're trying to combine kind of the 48 contiguous states and then information related to Alaska, Hawaii, and the territories in the case of WIC, is kind of pull that over to the right-hand side and share that information in a nice simplistic way. So these are still color-coded the same way as the overall map, and share the same information around how many participants are participating in WIC. A user can also toggle between looking at the map with WIC participants or looking at COVID-19 cases. So we're now over 9 million COVID-19 cases in the United States as of November. And similarly, you can kind of hover over this information and see how many cases there are per state. So after a user kind of plays around with this main dashboard, a user can then click on an individual state to view more information related to how WIC is changing. So I'm going to click on the District of Columbia to start things off. So one of the things that we wanted to do when we were designing these dashboards is give states the flexibility to share with us the information that they had readily available, but also present a consistent series of information across all the dashboards, so a user wouldn't be lost when they were looking at these dashboards. So how we did that is the left-hand panel of the screen that you're seeing right now has consistent information across all of the state agencies that participated in this project. So the first thing is information on trends in COVID-19 cases, unemployment claims by week, and then WIC participation by month. Those three pieces of information are consistent across all of the dashboards. And then the rest of the dashboard is focused on information specific to that state agency that they were able to provide. So for example, in DC, there's been about 17,000 COVID-19 cases. This graph that you see is showing cases by day, and it's a 7-day moving average. So you can hover over that and see how the cases change over time. And then the orange bar, we wanted to highlight when stay-at-home orders were issued. So that kind of shaded spot that you see shows that on April 1st, 2020, the District of Columbia issued a stay-at-home order, and then that order ended on June 8th, 2020. We keep that pattern throughout all of these graphs so that you can see when there were spikes or changes in cases, unemployment claims, or WIC participation by month. The rest of the information is specific to the data that the District of Columbia had available on WIC. So a user could go in and kind of explore where WIC participants are by zip code in the District of Columbia. And you can go in and highlight a particular zip code of interest as well. Then over on the right-hand side, we also have trends in WIC check redemptions. What that means is how often are these participants using the money given them to purchase foods. And an interesting trend that we're seeing is WIC participation has remained steady or increased since the start of the pandemic, but WIC redemption, so when they go and get food, has actually decreased. And one of the reasons for this might be concerns about going to the grocery store, for example. So it's an interesting trend that we've seen as we've studied this data over the past few months. I'll also note DC WIC data always has kind of a 2-month lag. So we have, the most recent we have for DC is July WIC participation data. I'll jump over to Idaho next. So this Idaho dashboard on the left-hand side, you see the same information related to COVID-19 cases, unemployment claims, and WIC participation. You can see that there's been a real big increase recently in COVID-19 cases in Idaho, but there's been a decrease in unemployment claims. And WIC participation, which you can see down here, has remained relatively stable throughout the pandemic. One of the most interesting pieces of information that we were able to get from our state agencies was related to what are called enrollment ratios. So that's the ratio of percentage of the percentage of individuals who participate in WIC out of all individuals enrolled in WIC. And that's what this kind of heat map table is showing here. Is it's showing that there's been a real increase in that since the start of the pandemic. The denser color indicates a higher percentage. So what that means is more people are participating out of those totally enrolled. So I'll hover over that so you can see that information. Idaho also provided information on trends over time by county. So you can hover over a specific county and see a map that shows trends in enrollment by month and the number of redemptions in that county. So I'm just hovering over here. And again, that orange bar that's in the center of that graph is showing when the stay-at-home order was in effect. Okay, and then I'll jump to North Carolina real quick. We loved working on the North Carolina dashboard because they have a lot of counties, and it was really fun and exciting to be able to explore trends and patterns in their enrollment ratios in North Carolina. So I'm just hovering over that information real quick so that you can see it. And again, you see that similar pattern in enrollment ratios over time. That increase, real sharp increase in North Carolina, which we saw similarly to Idaho as well. And you also see an increase in online referrals related to WIC starting at the beginning of the pandemic. And again, that stay-at-home order as well. Users can kind of filter between different views, and the trend line will change at the bottom. And then I will jump over to Vermont real quick as well. So Vermont has the same information again on the left-hand side, similar information and patterns that we're seeing related to enrollment ratios over time. You can hover over the map. And what's interesting about Vermont is Vermont provided information related to not only enrollment ratios, but redemption ratios. And again, there's actually this interesting trend appearing here where you see increases in enrollment ratios, but decreases in those redemption patterns. And then for Vermont, you can select information to view redemptions by food category, and a user can go in and kind of change the view depending on the food categories that they would like to see. And then the last one I'll jump to real quick. I know I'm moving through this pretty quickly, but just wanted to make sure if there were time for questions, happy to answer them as well. This one is for Wyoming. So this is the smallest state that we were kind of looking at related to WIC participation. Wyoming did not have a stay-at-home order in effect, which is why you don't see those orange bars in the line charts in this figure. And what we did for Wyoming is they provided information down to the zip code level among participation in WIC. Given the small size of Wyoming, we did mask a number of the WIC agencies in Wyoming, but you can hover over and see the breakdown by participant category. The size of the bubble on the map indicates the size of the participants. And then similarly for Wyoming, we also have information on food category. So you can kind of hover over that and see trends in participation among food categories, and then trends in participation over time over the past few months. So with that, I will return to the home page, and I will, I'm actually going to stop sharing my screen, and I'll turn back on my video just to see if there are any questions. I don't know how, Gwen, I don't know how much time we have for questions.
So your talk's supposed to end at 10:30. So we have time for questions, and we're in fact ahead of schedule. So you've done really, really well. We're congratulations. You get the gold star for today. So we do have one question from, I'm sorry, I'm gonna probably not mispronounce this name, but I'll do them best. Shmuel Yeshurlam. Anyway. So they were wondering about the accuracy of the data in COVID-19 in the sickness data for COVID-19 for District of Columbia.
Sure, yeah, so this data is all from the CDC. If you kind of Google trends in DC, you'll see similar patterns in terms of the total case number. So a couple quick notes, the number that's being displayed is the total number of cases. The trend over time is a 7-day rolling average to just minimize any spikes you might be seeing.
Okay, thank you so much. Hari Chan was wondering if you could share the WIC dashboard link.
Sure, yes, I'm happy to share that link right after my presentation, and feel free to take a closer look at that. We have Insight also post some other publicly available dashboards on our Tableau Public site. So for folks that might not be familiar with Tableau Public, you can create visualizations in Tableau and then create just like a user profile and share any visualizations that you would like to have publicly available. It is important that you know that that data is public, but that is just a great resource if you have visualizations that you kind of want to showcase your organization is doing.
We had another really great question from Marshall Furman, who said it was a wonderful talk and thank you very much. And they wondered about the iteration in your dashboard and the process of how you went about designing it.
Ah, such a great question. There's There's two things. So one of the things that we did is we first just met with this user group of WIC state agencies and said, what data do you have readily available? We did not want to make this a challenging process for the state agencies, given that we were in the midst of a pandemic and they were learning how to operate in that. So what we did was we met with them and just said, what kind of questions do you want to see? So I'm going to talk about North Carolina real quick. North Carolina did not have staff that were able to take the data that they had at the county level and visualize that in a map. So when we did that for them, they were not only able to quickly view 100 county data levels, like you could see it in a map a lot easier than going through a spreadsheet that had 100 tabs if you could put it on a map. So we were able to show them that and work with them on kind of that piece of information. We designed all of the dashboards individually and then met with each state to say, is this kind of interest to you? Is this kind of something that you want to be seeing? And then we adapted based off of that. Every month, so we posted these live in April, June, I believe, and we've been continuously updating them each month with data that we get from the state. So we now have kind of a process on our end. We're using our scripts to kind of clean and structure the data before we upload it into Tableau. We do the same thing to pull the data on unemployment claims for the Department of Labor, as well as the COVID-19 cases for the CDC. Great question.
Okay, we have a few more questions. Stephanie Tsao is wondering if you can talk about the challenges of making the dashboard by state, given some states show different types of data. So, yeah. And they love the use of colors and the design given there, and there's a lot of information packed into the dashboard. Can you talk about how you decided what data to leave out to keep each dashboard not too busy?
Oh, yeah, that's a great question. That's a really challenging question. So one of the things we wanted to do is always have the same consistent pieces of information on the left-hand panel. So that was kind of easy to decide. All the state agencies had participation information, DOL had unemployment claims information, and the CDC had the COVID-19 case information that we were able to pull. So that kind of, once we figured that piece out, that was nice. One of the things that we then wanted to say is we have text that I didn't really talk about, but we have text at the top of all the dashboards that tells the reader what they should focus on for that state, and that varied state by state. After that, we just use we generally used what the states provided and then tried to elevate the key themes and trends and patterns that were the most interesting. And a lot of that was related to participation by participant category, so women, infants, and children, or those changes in redemptions where folks are, it appears, to be more hesitant to go to the grocery store, for example, to get food. There might be a lot of other things going on there, but we do see this kind of decline in redemption patterns across several states.
Okay, thanks very much. I still think we have time for one more question. And it is regarding decreasing redemption rates. What is the WIC redemption process? Does it involve higher COVID risk than other grocery shopping? If so, could states modify that process to mitigate this?
Oh, that's a great question too. So no, you can use WIC at any, well, I shouldn't say any normal grocery store, but most normal grocery stores you can go and use WIC so no different risks than individuals that are not on WIC. However, WIC can't be used online right now, so that's one of the challenges too. We have you can shop online, but WIC can't be redeemed online, so that's one of the challenges.
Okay. Thanks so much, Kelsey. We really appreciate your talk, and it was really, really wonderful. I think we'll just go on to the next talk right now.
Great. Thanks, everybody. Thanks for the questions. Thanks, Gwen.
You're welcome. Okay, so James Cutler is up next. He is going to present a wonderful presentation on modern data science techniques for visualization.
Can everybody hear me, or anyone?
I can hear you fine, James, so thank you.
Thank you, and I'm hoping it's wonderful. Hi, I'm Jim Cutler. I've been doing data science for about 14 years now, and the last year and a half I've been with the Department of the Army as a civilian, and I want to thank you all for your time. Next slide, please. I'm not going to give an overview because of time constraints, but I do have some introductory remarks. If nothing else, you can decide, hey, I'm going to bail for 20 minutes. Again, in the interest of time, I won't be going into much detail on the slides, but I hope that they provide all the detail you need to understand and use these visualizations. Throughout, I'm going to use the term black box model, which simply means that you cannot easily understand how the model produces its predictions. This presentation focuses on general tools to explain these black box models rather than on how to present a particular set of big data. And why is this interesting? Well, in general, the choice that you have to make is this. Do I use a black box model that gives a more accurate prediction, but that has to be explained on a case-by-case basis? If somebody actually cares, or do I give a less accurate prediction using a model like linear regression that is easy to understand because it behaves the same for all cases? I'm going to show you some of the ways you can understand the predictions and the macro behavior of the black box models. As a final note, I'm only showing our visualizations, but these are also all available in Python. Next slide, please. In my experience, the coefficients on the left there are the main reason that most non-data scientists want to use regression. At one point, I was working in a grocery store, and they wanted to know if I increase my square footage by this much, how much more money am I going to make? So they wanted linear regression. But coefficients are often quite misleading, as perfectly linear relationships are uncommon in the real world. Also, non-data scientists often confound the magnitude of the coefficients on the left with the t-statistics on the right. And as you can see, there's quite a difference. Next slide, please. The title lists some of the problems that evoke groans from practitioners of regression. I can tell you that I have groaned many times with these, but that most modern data science algorithms are practically immune to because their creators build in as much automatic immunity as they can to these and other problems, making your life a lot simpler. For instance, looking at the residual plots and the linear regression on the left and XGBoost on the right, you can see that they both suffer from heteroscedasticity on exactly the same data. The big difference is that heteroscedasticity causes the theoretical underpinnings to break down for linear regression, but has no impact whatever on the theoretical underpinnings of XGBoost. And now let's take a closer look at how these two models actually compare. Next slide, please. You can see that XGBoost is way more accurate. It's the little blue line there where you can't even see the spread. Now, how hard is XGBoost to learn? Well, I worked with an intern a while back who had only 3 months, of data science experience and only 3 months of our experience. That's how he learned his data science. On his own, he implemented an XGBoost model in R for his own data using samples from the web in less than a day. He obviously did not have the data science background to understand many of the advanced features of XGBoost or use them, but he was able to get excellent predictions without needing to understand them. Next slide, please. I don't unfortunately have time to explain trees and forests, but they're easy enough to look up. I mentioned extremely random trees just to make sure you know there are many different kinds of trees and forests. Next slide, please. For forests, there are 3 different ways to measure the importance of features. As you can see, the different measures can vary very much in how they assign relative importances. So if you have time, it would be good to investigate all 3 so that you can choose the one that really meets your particular needs. However, if you just want to use a measure, you do well to use gain. Next slide, please. On this radar plot, you can see how the various gains, that is feature importances, compare. Next slide, please. Most of this presentation is on SHAP because the bottom line is, aside from image handling, SHAP is currently the best general purpose tool to have in your belt for most use cases, even for text processing. The important thing to know is that SHAP comes from game theory. It's many decades old, and hence fairly, in game theory terms, apportions the causes of a prediction to the features and their interactions. Next slide, please. The SHAP waterfall plot is probably the most useful visualization for explaining individual predictions. The starting point at the top there, kind of towards a little to the right, is always the mean of all the actual Y values. Each horizontal bar then shows you for this particular observation what the feature does to the prediction. decreases it or increases it. The features are arranged vertically from largest to smallest effect. As you can see from the 6th row, SHAP will automatically include interaction terms so that you can get an idea of when interactions actually have a big impact on your prediction. The purple bar at the bottom shows the cumulative effect of all the things, and so its endpoint is where the actual prediction value is. Next slide, please. Here we have the min and max predictions from this particular set of data to demonstrate what I'm sure you're all familiar with, lying with statistics 101. Note how the range and scale of the x-axis differs for each of these two observations. Note how the same position on the y-axis can be for different features because they are sorted by the magnitude of the effect. And finally, both the bottom bars are purple, even though the cumulative effect is negative for the min prediction and positive for the max prediction. Next slide, please. With the SHAP force plot, we're moving away from the waterfall's delineation of exact composition of the predicted values to consider only the relative importance of each feature for each observation. A feature being above the axis means that it increases the prediction and vice versa. Note that some of the features can be both above and below the x-axis, while others are always on one side or the other, and the size of the feature can vary widely from prediction to prediction. Next slide, please. This is the same as the last chart, but it's for all observations instead of just the 12 that I randomly chose. It gives you an overall feel for feature importances. Next slide, please. We've already seen the two charts on the left and the middle. The rightmost is just a variation on them showing individual observations in a grid if that is more useful to you. Next slide, please. SHAP value plots allow you to dig into how the value of a feature changes its importance to the prediction. The low S curve, that is the red line, is great for giving you a feel for the general trend. Next slide, please. Here we have the SHAP value plots for all features, and I'm showing them simply because, as you can see from the low S curves, the features vary greatly across their, or their impact varies greatly across their values, and no two are alike. Next slide, please. With SHAP dependence plots, we're getting into how the SHAP value, that is the importance for feature A, varies with the value of feature B. That may or may not be something that you want to investigate. It's not the same as interactions, and we'll get to those in a moment. In this chart, each dot is an observation. For each dot, the Y value is the SHAP value of feature A, and the X value is the value of feature B. And the color is an indication of the value of feature A. We get a low S curve as a bonus. Next slide, please. Here are the SHAP dependence plots for a single thing, lamotrigine, against all the other features. Notice that no two low S curves are alike, once again. Next slide, please. Now we're finally moving into feature interactions, which is very interesting, generally speaking. The SHAP feature interaction heat map is a good starting point for investigating feature interactions because it gives you a 10,000-foot view of the magnitude of the SHAP values for the interactions of each pair of features. Notice that the chart is not symmetric. This is not a bug. It is simply, you can go back to the SHAP slide and see that that's just the way SHAP values work, although it's compensated for other than in this particular chart. Next slide, please. Once the heat map tells us which feature interactions are the most interesting, we can do a deep dive on pairs, or all of them if you've got the time and the resources, using the SHAP interaction plots for the feature pairs of interest. Again, you have a low S curve. You read it just like the SHAP dependence plot, except that the y-axis is now the SHAP value for the interaction of the two features. And as we discussed in the previous slide, reversing the roles of the two features can drastically change the chart because in actuality, it does actually change the interaction impact. Next slide, please. The SHAP summary chart takes a little getting used to, but is a good way to get an intuition for how feature values impact predictions. This is an alternative to the SHAP force plot, and I've included that as an inset just so you can see the difference. It's fairly easy to understand. You can read the text on the slide there. Next slide, please. We're leaving SHAP behind and moving on to Lime, an entirely different product. It's newer than either SHAP or the other thing that I'll cover in detail. Lime is currently only implemented on forests, text neural networks, and visual neural networks, but the techniques, according to the authors, can be extended to other black box methods, and efforts are underway to do so. Lime works by changing the values of the features and then measuring the change in the predictions. The next method we'll cover does value changes differently, and so it's important if you're deciding between the two to understand and choose the one that you think is more reasonable or important for your particular use case. There is, by the way, a nice interactive app for text analytics from the Lime authors that you can access from its R Vignette webpage. Next slide, please. This is the Lime output for a single observation. Lime does not currently support feature interactions. So unlike SHAP, where you just automatically get to see the important ones, you're on your own. You'd have to create a feature that had the interaction and then see what Lime said about it. Let me emphasize that the weights are not like SHAP values. There cannot be a waterfall chart with Lime. The weights do not add up to the difference of prediction from the mean of Y. They just indicate how badly messing with the value of the feature will affect this particular prediction and whether it will increase or decrease the prediction. Next slide, please. This is a grid of plots for individual observations. Everything from the last slide applies to each individual plot. Again, I'm showing this to remind you to be careful of lying with statistics 101. Everything about the y-axis labels can change from one plot to the next. Next slide, please. My apologies. I changed the heat map at some point and forgot to change the text, so they're not quite in sync. The Lime combined heat map plot gives you a general feel for the magnitude of the feature importances across observations so that you can dig deeper into what's going on. Next slide, please. The last technique I'll cover today is permutation feature importance, which was around before either SHAP or Lime by a long time, but is not necessarily replaced by them. You should keep the weaknesses mentioned in bullets 3 and 4 in mind if you're going to use it. They're very important. A chart is not shown, but it can be easily produced. Next slide, please. Visualization of black box models is a rapidly expanding field. I could have had 200 slides and not covered everything. And there are lots of options that I haven't covered. Many big names have thrown their, as you can see on this slide, have thrown their hats in the ring. A lot of them cost money as compared to these that I'm showing that are free. But here's a starter set for your web searches if you want to find out more and investigate the whole field. Next slide, please. Here are just some random thoughts and opinions from me that I won't address except for the third bullet. Modern data science algorithms are, XGBoost especially, is being presented in many cases as a way to, for just any old person who knows nothing about data science to get good predictions, sort of like my intern did. But modern data science algorithms are so powerful that they can memorize your data instead of learning to predict. If you're going to use these modern algorithms, you have to understand the concepts I've listed on this slide. If nothing else, you should look up the term overfitting so that you understand this memorization versus prediction. Next slide, please. Again, I'd like to thank you for your time and wish you all the best in your careers and lives. Before I open for questions, let me point out that the last slide, which we won't show, is an appendix with a list of the R packages that I use to create these charts. Thank you.
Hi, James. Thanks so much. We do have a number of questions, and you did so well. You also finished within plenty of time. So you're not supposed to until 10:50. We still have another 7 minutes. So I'm so happy that everyone is going ahead of schedule.
So I'm a runner-up for that prize?
We don't do it like they do it in the Army. Everyone wins here, okay? So I'm really sorry. I'm sorry.
Okay.
We're not as competitive as you'd like, but anyway. So we have a great comment from Carol Robbins that says there are excellent predictions that can't be explained, are hard to use for decision makers. And I just wondered, do you have anything you want to say about that, or?
Yeah, that is the problem with the black box models, right? But again, it goes back to if they really care about a particular prediction, like in my case in retail, right? I could say on a particular store, hey, it's not the square footage that really makes a difference, even though that's what you want to say it is. It's more that it's the fact that it's close to a freeway or whatever. So that is the trade-off you're making. Linear regression is great. I mean, it does, but it is a straight line. All the regressions are straight lines when it boils down to it. So you're depending on a linear relationship or a transformed linear relationship to represent something that probably isn't one.
Hmm. Okay, we have another comment from Charles Coleman, and he's talking about the Shapley value for models is explanatory. If you're concerned with prediction, the proportionate value is better and is used in conditional forests. Do you have any comments or anything that you want to share about that?
No, I don't know that I can see the point, but he's probably right.
Okay.
I mean, certainly, let's see, I don't know. I don't know how to give him my email, but I mean, I'd certainly love to discuss it offline, but I think that's, that's not like a 1-minute answer. So.
Okay, we have another comment or question from Shmuel Yershalmi. I think I'm better the second time through that time, Shmuel. And his question is, if a SHAP model can be used for civilian goals, or is this specific to the US Army?
Oh, it's absolutely civilian. It's open source code. The particular ones that I showed were built into the XGBoost package, but SHAP is an R pack, or there's any number of packages that have it built in as well. And Shapley values are just, you can get an independent Python package, an independent R package, and use it for whatever you want.
Okay. Okay, so go ahead.
Oh, so I was going to say the same is true of Lime, and the others are, well, other than the ones that I listed. I don't know that they all cost money, but most of them do, right? Those are like for-profit companies like IBM. So I can't imagine their products are free.
Yeah. Okay, so Kelsey Gray has, who was a speaker just before you, she says,
Yes.
I love the idea of being able to visualize black box models. Are these applications being used by the US Army now?
I can't speak for anything outside of my particular group, and yes, in my particular group.
Okay, let's see.
Saying
Do we have
until this whole situation comes
and Chuck Coleman
you.
actually posted his email in the chat so that you could
Okay.
discuss this conditional
Great.
forest question.
Hi, this is
And you can
Alright.
also post yours in the chat.
So please do not
And
close the
I
meeting
think
quite yet.
we're 3 minutes early, and I think we'll just go ahead on to our next speaker. So thank you so much, James. Really, really appreciate you. You and Kelsey both get a gold star today, and good work.
Thank you.
You're welcome. So our next speaker is Mithili Krishnan, and he's going to talk about analyzing global COVID-19 data with data visualization.
Hi everyone. Are you able to hear me?
Yes, I hear you fine. I don't see any slides though. Do you know how to share? You know what to do there?
I'm just sharing my screen.
Excellent work.
So let me know once it's.
Yes, I see it. Yeah, excellent. We see it all. Thank you.
Okay, thank you so much. So without further ado, let's get started. So today I will talk to you about how to do some COVID-19 visualization analysis. And this is going to be the agenda. So I'll briefly talk about myself. What is COVID-19? I'm sure everyone knows that. What exactly is a choropleth map? We'll talk about Folium and Plotly briefly. Then the analysis that I'm going to share. Post that, there will be a short code demo and also further references. So yeah, so here's about me. I'm actually a master's in economics from Delhi School of Economics, and I'm a vice president working with Accenture, and I have a diverse industry experience in data science solution in different domains like financial services, large platform clients, telecom, etc. I'm also the recent winner of the 3 AI Pinnacle Awards 2020 Women in Analytics and AI category. And I'm also an inventor of about 4+ patents in the areas of application, failure prediction, forecasting, and other domains. And I also write research papers in the areas of machine learning and data science. And these are the links to the deck that I'm showing today. And also, this is the link for the demo code. So in case you want to kind of like use it later. So yeah, so about COVID-19, I'm sure COVID-19 needs no introduction at all. So everyone knows it is the infectious disease which has gripped about like more than 219 countries across the world. But how do we actually visualize how the world has changed over the past few months? So can we use certain simple visualization techniques to analyze the spread? And that is exactly what I am going to talk to you about today. And so first, let me talk to you a little bit about what exactly are choropleth maps. So choropleth map is actually a type of a thematic map in which areas are shaded or patterned in proportion to a statistical variable, which represents an aggregate summary of a geographic characteristic within an area. So it can be like a population density, it can be per capita income. In our case, it will be the COVID confirmed cases. And there is actually a lot of easy way to visualize how measurement varies across the geographic area. It's similar to a heat map or an isothermic map, but it does not use a priori geographic areas. And there can be two main types of choropleth maps. So it can be classed or it can be unclassed. And we can decide on the classes based on the distribution of the data with the help of a simple scatter plot or a histogram. In unclassed choropleth maps, each unique data value gets a unique color. For example, the COVID confirmed cases for the different countries of the world would be ranked from lowest to highest and placed along a continuous color ramp from low to high. For example, there is a big numerical gap or jump from a country with, say, the third highest COVID confirmed cases to the second highest, and correspondingly, there will be a larger jump in the color. So we will see this later on when I show you the actual demonstration in the code, that how the data is arranged proportionally with respect to these colors. So we can use unclassed choropleth maps whenever we want a less filtered view of our data. And when we can't find a good classification scheme that does the data justice. Or when we are making a map specific to certain overall geographic patterns. And when we can use classed choropleth maps is when the data attached is to enumeration units and we want to show both the overall geographic patterns and also make it relatively easy on our map readers to extract certain specific data points. So in that case, we can use classed choropleth maps. But I mean, like there are pros and cons of both. In this case, I will show you the unclassed choropleth maps. And two important things that we will require for creating the choropleth map is geospatial data like a GeoJSON file or variables or data points which can be used for the color coding. So these are the two important things that we require. So now today, actually, we will be using two different Python libraries for plotting these choropleth maps. So one of them is Folium. Folium is a library in Python which can be used to visualize geospatial data. And Folium makes it very easy to visualize data that has been manipulated in Python on an interactive leaflet map. Leaflet.js, so this is the JavaScript library, for creating the maps, and Folium combines the functionality of Leaflet along with Python's data wrangling abilities, which is like leading, transforming complex data sets. And it can create like really beautiful interactive maps. And also it can enable markers with HTML visualizations. And different map projections are available like orthographic, natural earth, and you can use different map tiles like Mapbox or Stamen Toner or ColorDB, Stamen Watercolor. So depends, I mean, like there is a wide range of choices. So that's about Folium. The second library that we are going to use today is Plotly. So Plotly is an open source graphing library which can be used to again create beautiful interactive graphs and visualization. And it can also be used to create HTML visualization with great animations. And as with Folium, the graphs are also interactive, and it is built on top of plotly.js. That is also a JavaScript. And the visualization can also be saved as an image. And it comes with a lot of customization and styling options, and the implementation is also pretty simple. And there's also a Dash, which is an open source framework. So I have given the link here. So in case you want to read about it more, you can actually take a look. Now, what are the analysis that I'm going to share today? So first part of the analysis will be how to plot the corporate maps with Plotly and Folium. And second part of the analysis, I will show what has been the effect of lockdown in two countries. And I will take here two examples of Italy and India here. So now I will go into the demo code for Python and show you how all this will work. So here is how you can get started. First, we need to import the libraries. So here I have imported libraries like Pandas, NumPy, Plotly Express, and Folio. We will take the Johns Hopkins data set. So this is a COVID-19 data set that is easily available in the Johns Hopkins University site. And we will actually use this URL, and we can actually read it in terms of data frame with the help of pandas. And if we check the data, so here I have selected the tail of the data, which means I am looking at the last 5 observations. You can see this is, it has the date, country, confirmed cases, recovered cases, and deaths. So, and also the beauty of this code is, if you run it tomorrow, you will actually get the most recent data. So since I ran it today, so I have data till 5th of November. For some countries, it is not updated till 5th of November, but you like for Zimbabwe, it's till 3rd of November. But whenever you run it, so it depending on whether this data gets updated, so you will get the most recent view of this analysis. So now to go into the part 1 of the analysis. So first we'll use Plotly. So this is a very simple code that we can use. So DF is the data set that we just read here. Locations will be country. Location mode will be country names. And I will use color as confirmed, which is the confirmed cases. And also animation frame as date. So once we run this code, so I've already run this code in the interest of time. And you will see here, this is how it looks. So I'll just go to this animation screen from the start. So as you can see, it started here with China. And you can see on the right hand side how the numbers are increasing as the kind of like the date is progressing. And gradually it's spreading to the entire world. So I will just fast forward it a bit. So as you can see, it has already spread to Europe, it has spread to Americas, and already there's like 500K cases. So I mean, like you can actually see according to the color map. So this is what I was actually talking about. So here, the most cases are colored yellow. So which is, I mean, like now it has reached million. And the cases, the lower cases are given a color gradation. So I mean, like dark blue color or the purple color are, I mean, like lesser number of cases. So I'll just fast forward it a bit. So now you can see it's still increasing. The second thing that you can do here is save this corporate map in terms of an HTML file. So this is the code. You can use Plotly offline for doing this. And if I simply run this code, so as you can see, we get this plot here as an HTML file, and you can actually use the play button and it will show you the, again, the same view here in an HTML version. Okay, so this is how you can use Plotly to do the corporate map. So now I will show you another library, which is the Folium. Here we have to, it's not that straightforward. So we have to do certain steps to kind of like get to the final map. First, we need to create a base map, and we will use Stamen Terrain tiles here. So you can read about all the different tiles in the Folium documentation. So map is the object that I'm creating, and tiles and minimum zoom. So very few options that I've used here. And when you display the map, so this is the world map that you see. So this is our base map. Now we need to obtain the geodata. So geodata is also available. This is the world countries JSON file, which gives the location of the countries. So you can actually access it from this URL here. So we will first read this URL, the JSON file, and then we will generate a corporate map layer. So you just have to use this code, and I will quickly show you what are the options that you need to use. So you can use country shapes, zoom, you can use whatever you feel like. I have used two here. I'll give COVID-19 the name, and columns is country and confirmed. And fill color I have chosen as orange and red, and none means wherever there is no data, that will be shown as black. So like you can see here, I don't have, the data is not updated for North America and uh, parts of Greenland. So it's black in color, but the rest of the data is orange or red in color. So here, the map is still not ready because I don't see any markers that we saw earlier with the Plotly map. So quickly, what we can do is we can also generate the markers. And for that, we have to get the latitude and longitude of the countries. So this is a CSV file I have read, which gives the latitude and longitude of all the countries. And I will merge this with my earlier data, the COVID data. So then the data set that gets created will have my confirmed cases, country, date, recovered, deaths, as well as the latitude and longitude of the countries. Now we'll just define a function for the markers, and I'm using custom markers here, a circular marker. And so basically we want to look at the country, confirmed, and recovered cases. So these are the points I want to actually mark in the graph. So I just apply this function onto my earlier map, and here you can see the markers are created, and these are, I have highlighted India here. So you can see the confirmed cases, and you can also see the recovered cases. And if you want to go to some other points like Libya, you'll also see, you can do that for any of the countries that you want. So that kind of completes the first part of the analysis, and this also you can save here as I showed in the form of an HTML format. You simply do map.save and a location, it may be in your C drive, and you can save it there. Now, part two of the analysis is let's look at like how severe the infection is with respect to a specific country. So here I have taken Italy, and I will just extract the data for Italy and from the world data that we earlier had, and we'll just look at the head and tail of the data. So as you can see here, we have data till 5th of November. And out of that, we specify some columns, the date column, confirmed, and the deaths column. And so this is how the data will look like. And we calculate the infection rate. For that, we take the first derivative of the confirmed column. And as you can see here, now we have the infection rate here. So if we plot the infection rate for Italy, you can see this is how it looks like. So initially there was a lot of cases, then there was a dip, and it again started picking up about September, middle of September onwards. So this is how the infection rate is for Italy. Max infection rate is about 31K. Now, what if we want to do this for all the countries? We can easily do that. So for that, we have to create a list. We create a country list, so which gives us all the countries. And we also have to do it unique because there is a repetition in the rows of the data. And then we create something called max infection rate. So max infection rate is just the first derivative of confirmed cases dot max. And then I have to just run it into a loop and print out all the max infection rates. So this is how it looks like. So I know that my code works. And then I put it into a data frame. So then the data frame would look like this. So you can see Afghanistan has 915, Albania has 381, and so on. Now we plot this with the help of Plotly. So PX is the acronym from Plotly, as we had imported the library. And we do this by the color for each of the countries, and we get a graph like this. So as you can see here, you can now see max infection rate for different countries. Like France has about 124K. Then this is Brazil, which is like 69K. So it has all the countries, and you can see the infection rate. So if you just hover around, US has about 99K. You can see all the values. So this is some quick analysis. You didn't need to do a lot, just by simple visualization. Quickly going into the lockdown
you
effect.
have 5 minutes. I'm just
okay.
I heard that no one heard the bell, so there was a bell. It's 5 more minutes.
Okay, yeah, I'll be done in 5 minutes. So, the analysis of lockdown effect in Italy. So lockdown was imposed in Italy on 9th of March. So we will examine what happened like post 1 month. So 2 dates I have initialized here, and I'll not go into the details of this code, but I mean, like if you read it, it's actually very simple. So if you plot it, this is what you'll see. So this line gives you when the red line gives when the lockdown was imposed, and this purple line gives you 1 month. And as you can see, lockdown did have an effect on Italy, and you can see the curve actually kind of like flattened. But then, as we saw in the infection rate graph earlier, it has started peaking. But yeah, this is what so lockdown definitely seemed to have an effect in Italy at least. If you look at the death rates, so again, you can take a first derivative of the deaths column. So you will get the death rate, and if you plot it, so this is how it will look like. But because these are in different I mean, like different values. So obviously we'll have to normalize this data. So we just normalize the columns and plot it. So this is how it looks like. So very interesting observation is in the initial period, the death rate was really, really very high compared to the infection rate. But now, I mean, like you can see the confirmed cases are peaking up, but thankfully the death rate is actually not that high. So that's actually good news. Now, the effect of lockdown in India. India had 4 phases of lockdown, and there was phases of unlock 1.0, 2.0, 3.0, and 4.0. Similar to the analysis that we did. So I'll just show you the final graph, how it looks like. So this is how it looks like. So it seems that lockdown didn't have an effect at all here because the graph kept on peaking. So that's what I had today, and these are some references which you can actually look at, and this is how you can reach me. I mean, like if you want to kind of like chat about it more, or you have any questions. And yeah, thank you. I hope I'm on time. Any questions? I'm happy to take it now.
You were excellent. We still have a few minutes to spare just for questions. So thank you very much. It was, I think, a very fascinating presentation, and I really appreciated all the use of maps and Plotly and Lisa. I don't know if I don't think I've seen any questions from any of the attendees or the panelists yet, besides a comment that said it's very useful. Thank you very much. If anyone has any questions, could you share your contact information one more time? So that's something, perhaps you could just put that in the chat. That would be, people would really like to connect with you. But I think it's time for us to, and someone says, thank you very much for including the code. So we really appreciated it and very much enjoyed your talk. Our next speaker is Cecile Murray, and her talk is going to be profiling statistical programming language performance for large-scale data tasks. So, Cecile, we're really looking forward to your talk, and thank you.
Good morning, everyone. Can you hear me all right?
I can hear you fine.
Great. So, my name is Cecile Murray. I am a data scientist at the US Census Bureau. And today I'm going to talk to you about some work my team at Census has been doing to sort of benchmark the performance of different statistical programming languages on some common analytical tasks. So before I get started, I do want to note this little disclaimer at the bottom of the slide, which is that the views expressed in this presentation are the views of the authors and not necessarily those of the Census Bureau, sort of a standard government disclaimer there. Next slide, please. So to give you a roadmap of what I'm going to talk about today, I'm going to provide some context, give you a little background for sort of how we came up with this exercise and what our research question is really focused on. Then I'll talk a little bit about the data and the methods that we use to actually explore that question. I'll present some results and the initial conclusions that we're drawing from those results. And then I'll talk about how we're going to push on this work going forward, so to describe the future work that we have planned. Next slide, please. So for context here, researchers at the Census Bureau, we work with large-scale survey microdata on a custom high-performance cluster environment. So to give you an example of what we mean by large-scale survey microdata, we could be working with the universe of decennial census responses from, say, 1990. That alone is going to be 249 million observations. And if we bring in microdata from other data sets that we have, other surveys, it's only going to go up from there. So there's definitely a scale challenge here that we have to confront. Most researchers and folks at Census work in SAS, but there are a really wide variety of research questions and empirical methods being applied, but regardless of the language and sort of that research question or method, researchers often perform similar data preparation tasks as they start their work. Some members of my team were working on a project and noticed that common analytical tasks like loading data and merging things and producing counts took a long time to run in certain languages and not a long time to run in other languages. And by a long time to run, I'm talking hours or days. And those kinds of delays can be really costly to the agency. They really slow things down, and we want to make sure that we're using our resources as best we can. So that led us to ask this question. Next slide, please. Which programming language offers the best performance? So the four languages that we looked at are the four that are shown on this slide. That's R, Stata, SAS, and Python, because those are the four languages that folks at Census are using really at this moment. We're also interested in exploring performance in Julia, but there's not really an active Julia user community at Census right now, so that did not make this list. Next slide, please. So now to talk a little bit about the data that we used for this test. We were working with the 1990 full count restricted decennial census file for 3 states. And the way those data are structured will be familiar to those of you who have worked with public use microdata from census surveys, but I'll just cover it for those of you who are less familiar with it. essentially there are 3 files per state. There's a person file that contains information about an individual and the attributes associated with them and their responses. There are household files where each row represents a household and the information associated with household level responses. And then there's a geography file that contains information about the geographic area in which, you know, a given household and person it would be located. We worked with a subset of, you know, we didn't work with all 50 states or the whole universe of responses here. We worked with 3 states, Delaware, Nevada, and Kansas, kind of looking at a small, medium, large breakout. And you'll notice that the number of observations per state just about doubles between each state. Next slide, please. So to give an overview of the method that we want to use here in terms of measuring which language is going to give us the best performance, especially focused on runtime, we're going to define a set of common operations. These are kind of conceptual tasks. So as a researcher or as an analyst, you know, you have an idea, you have a goal in mind. What are you gonna, you have something that you want to execute. So we defined a common set of sort of operations that we wanted to execute. Then we wrote scripts in each language to do that. We ran those scripts using the same resources. So we had a 250 gigabyte compute node ready to run each of these jobs. And then we measured the performance of the script using the runtime in seconds and the percentage of CPU. Next slide, please. So to talk about what those common operations were, the algorithm was essentially this. For each state, we loaded the data in. And I should note here that, as I mentioned before, most users of this environment at Census are SAS users. And so the data are actually stored in a native SAS format. So for R, Stata, and Python, we actually did need to convert from that native SAS format before we can kind of load it into memory. So that's the first step. The second step is to merge the person, household, and geography files that I mentioned earlier, so that we have one flat file where it's a data frame, essentially, where each row is a person linked to their household and geographic information. So we know, you know, you're living in a house, you have these responses, maybe this is your age, this is your gender, and then we also have your household information on that, it's sort of in another column in that same row, and then we have the geographic information about where you're located in that same row farther down on sort of the list of columns. Then we just wanted to perform 3 pretty simple analytical tasks. We wanted to count the number of people in each household. So essentially there, what we're doing is we're counting the number of rows in that correspond to each unique household ID. Then we compute the mean number of people per household by state, and we compute the mean age by county. So these are all kind of summary operations, almost diagnostics that one might run when one was doing analysis. Next slide, please. And I want to emphasize here that we have one implementation per language here, because the question that we're asking is essentially, what would a reasonable user do on their first pass through this task? So if you're a researcher, you're an analyst, and you're coming to this environment to do your work, what are you going to write the first time that you write this script before you sort of have had a chance to see what might be quick versus what might be slow? So we're not trying to write in this first wave the fastest possible script in any given language or test a lot of versions of different scripts. We just want to approach the tasks in a way that seems really natural for each language. And that does mean that there are some differences in how we actually approach the sort of nitty-gritty step-by-step piece of each task. So for example, we use for loops in Stata and Python, but a map call in R. In SAS and Stata, we have macros. In R and Python, we have functions. We didn't really want to move too far away from the sort of the natural way in which a competent user would write in each language, because we want to sort of see how the strengths of what a typical user would write in each language stack up against each other. Next slide, please. So I do want to talk a little bit about that conversion from the SAS format. SAS users here, again, probably have an advantage because we do already store the microdata files in that native SAS format. So just to sort of describe how we converted that in each language that was not SAS, in Stata, we looped over all of the files to convert them to .dta, and then we read the .dta files and work with those. In R, we use the Haven package read_SAS function. And in Python, we're using pandas pd.read_SAS. So to move from describing the methods to talk about results. We can move to the next slide. That might not surprise you to find out that the SAS runtime was the quickest by far. So here I'm presenting runtime in minutes for each language, and you can see that SAS took just under 30 seconds to complete this task for all 3 states, whereas Python took something like 21 minutes, so something like 40 times more time. And you can see that Stata and R under 5 minutes, but still substantially slower than SAS. Next slide, please. When you break that out by task, so looking at the time that it took to complete each sort of chunk of work, you can see that the read in Python is what's taking so long. And for those of you who use pandas, this probably is not surprising. Pandas reading is known to be kind of slow. But you can also see that it's slow, the read is slow in R as well. So SAS and Stata have actually completed all of the work for all the states before R or Python have even finished reading in the data. Next slide, please. So then when we break this out, like there's very different scales on that last chart, right? So this chart just shows the percentage of runtime by task to kind of see how each language is spending its time within the time that it did spend. And again, on the bar in the far right shows that Python is spending the majority of its time reading. The other thing that stands out here is that Stata is spending a lot of time on that merge step. And this is where the differences between the languages get a little bit tricky. Task divisions are not exactly comparable, since Stata merges are, the version of Stata that we're using does not allow you to have multiple tables in memory at once. So you do have to interact with the disk when you perform a merge. And so that might be why Stata is spending so much time on that section. Next slide, please. This was just an effort to sort of look at this. This chart shows essentially what happens as the size of the data set goes up. So each of these sets of bars is for one of the languages from top to bottom: Python, R, SAS, and Stata. The x-axis here is showing the runtime in seconds, and you'll notice that those runtimes are different. So the x-axis is not the same here because the runtimes for each script are quite different. And then what you can see is as you go down within a small group of bars, you're seeing how much longer it takes the language to complete the task as the data set roughly doubles in size. And so you can see that most of these languages are actually starting to have trouble as you with scale as you get to that largest data set. Next slide, please. The last result here, I'll just show, this is the percentage of CPU usage by language. So for those of you who are not familiar with this metric, the percentage of CPU is a measure that just kind of shows you what percent of CPU cycles are dedicated to kind of actively running a process at a given point in time. So the x-axis here is the number of seconds elapsed since we started the script. And the y-axis is sort of what percentage of the processor is being actively used at that moment. It's kind of a measure of how intensely we're using the processor. And as CPU percentage goes up, you kind of expect to see performance go down. I should note here that x-axis is truncated at 350 seconds because Python's runtime extends far out to the right, but the memory usage for Python does extend essentially at that same level for the remainder of the time. But you can see here that actually SAS and R are using less CPU than Python or Stata, and that Python is really potentially having performance issues in part because of that really high CPU percentage. Next slide, please. So just to wrap up with these initial conclusions, SAS is the fastest and uses the least CPU. Python is about 40 times slower than SAS and has one of the highest CPU levels. We think that converting files out of the native SAS format is likely a huge contributor to those runtimes. I personally am a user of R, Python, and occasionally Stata, and not a SAS user. So it's a little bit depressing for me to see that my jobs are going to always run slower than SAS users' jobs, given that conversion time. Then we also noticed that Stata is pretty CPU intensive, even though it is fast, and it does spend a lot of time on this performing merges. So that's an interesting question about, how interaction with disk is influencing resource usage here. Lastly, we noticed R spends relatively less time on the merging steps and did not require so much CPU, but it spent a relatively larger chunk of its time on the actual analytical steps. So there might be room to kind of optimize the code as far as how that step is done. I'm going to go to the next slide. So just to talk a little bit about future work, I think two primary next steps that we're really looking at. One is to incorporate measures of peak memory usage. So in this presentation, I've showed you runtimes and I've shown you CPU percentage. We'd also like to know how much memory is actually being consumed, because we're doing this work on a sort of a shared cluster environment. It's a shared resource. And if we're using languages that are, consuming more than their fair share of resources, or consuming more resources than we need to, then we're using up resources that could be used by other people at the agency. We also want to experiment with measuring performance after conversion from SAS format, as I saw several folks pointed out in the comments or in the chat. We have an experiment planned where we've converted all of these files to CSV, and so we're gonna run the same thing using CSVs as the starting point rather than the SAS format. We'll sort of see what happens with that when we put all of the languages on a more level playing field. The next two sort of areas where we want to work on this are exploring ways to optimize code in each of these languages. I talked a little bit about that. I said, maybe there's a way to get some of that R analytical work to work faster. Maybe, using a different version of Stata would help us with the merges. Maybe there's a way of doing things in a different order that would run more quickly, stuff like that. But what we've done here is we've sort of written a benchmark script. And from there, we can actually see how those kinds of code changes affect outcomes in terms of runtime. We also want to explore parallelization to more fully leverage our HPC resources that we have. So these tasks are, if you're familiar with parallel computing at all, they are embarrassingly parallel in that they can be broken up by state across potentially multiple compute nodes run in smaller chunks. And that might let us not only run individual pieces more quickly because we can run them at the same time rather than running them sequentially, but we can also use our HPC resources more efficiently, in that we don't have to request one big chunk of a node. We can request small chunks of lots of different nodes. And so then the last
5 minutes.
Sorry?
5 minutes. You just have 5 minutes, and just would let you know.
Thank you. Yeah, I'll just wrap up saying that the last two areas where we want to sort of push this work forward are to benchmark performance with more complex analytical tasks, right? Because as interesting as means and counting counts are, they're important diagnostics. We're also doing more sophisticated analytical work. So if a certain language performs really well at those tasks, that's going to be really important as well. And then also to consider qualitative measures like the length and the complexity of a script, how modular the code is, who is using, what the user-based census understands, how easy it's going to be to maintain, in terms of making recommendations to our colleagues about, which language they might want to use when they're starting out a new task of a certain kind. Next slide, please. So I will leave it there. I'm really interested in hearing folks' comments and questions, especially if you've worked in a old statistical agency in a sort of similar custom environment with large data sets. Be curious to know what your experience is. Thank you very much for listening. I'm happy to take your questions, and also I've included my contact information and a link to the repo with our code in case anyone is interested in following up.
Okay, thanks very much, Cecile. You have generated a lot of questions here. So we'll start with Jose Bayon Santiago Calderon, who has a question that says, I would imagine SQL would be the most natural language for those operations. So do you have any feedback for him or any?
Yeah, absolutely. We would need a database engine in order to be using SQL in a more full way. So there is a way of writing queries in SQL in SAS and in Python and in R as well, sort of injecting them. But we couldn't use SQL by itself just because of the way that our custom environment is set up.
Okay, thank you. And then Joseph McGill has a question. It does seem obviously hard to compare these. Oh, but you already talked about the CSV issue. And then Kelsey, who spoke earlier, talked about the runtimes being fascinating, which I thought so too. Carrie Crohan has a question. Did you consider using hash to perform the merging?
Yeah, Yeah, I'm not actually familiar with that technique, so I'd love to hear more from Carrie about what is meant by that. Feel free to reach out via email or just in the interest of time, I'd love to hear what that suggestion actually is about.
Okay, so and then the next one is Christian Moscardi. Really depends on the user. Funny enough, for the other language it offers, the environment doesn't have an SQL database researchers can feed data into. It's all files. Researchers can set up an SQL-lite database as a stopgap, but it's more effort than you'd like to put in.
Yeah, Christian is my colleague, and again, that's sort of addressing the
I wondered that.
Yes.
I wasn't. That all the presenters' names went by so quickly. I didn't quite pick up on them all.
Absolutely, we have a large team of us collaborating on this one.
So Josiah says, when you refer to R and Python, which libraries are you referencing? The ecosystem is really vast.
Yeah, when we're talking about Python, we're mostly talking about pandas, and in R, we're primarily using the tidyverse package, as well as the Haven, sort of Haven for reading from SAS, and then dplyr, and I think there's some, yeah, sort of vanilla tidyverse packages are what we mean when we're using R. It's not base R.
Okay. And then Laura Thompson talks about, are you using lazy evaluation, which might be the delay in the CPU usage?
Yeah, I'm really interested in that. I was the author of the R script, and so I'd be very curious to rewrite it using a version that does not use lazy evaluation to see sort of what happens with CPU usage in that case.
Yeah. So I think we're just about out of time in terms of question, but there's a whole bunch right now. It looks there's so many questions. So I'm really excited that there's so many questions about this, because I'm just gonna do a quick plug, which is that I'm giving a talk at the DCR conference. They've renamed it this year, but it's in early December, and it's about vectorizing coding, which maybe something. It's about writing faster coding in R. So it might be of interest to some listeners. Okay, and to you. I think we're ready to end this session right now, and we'll go on to the next session. So I'm not sure who the next chair is. Mike, hopefully you can come in and answer that.
Hi.